Welcome to solverfy.
In this problem, we have light incident on a sequence of 3 different materials, each with a different index of refraction, N1, N2, and N3. These indices of refraction are given. N1 is 1.32, N2 is 1.75, and N3 is 1.39. We're also told that the wavelength, or the vacuum wavelength of the light incident here, lambda, is given to be 382 nanometers. And we're asked what thickness this middle material here has to be, so this thickness is labeled L, such that we have maximum reflection of light. And more specifically, we're asked what is the third smallest thickness that this material can have in order to have maximum reflection. So we'll get to that part a little later. First, let's just look at what happens, or what needs to happen in order to have maximum reflection. As light is incident upon this first surface, part of it's going to reflect, which is ray 1 here, R1, and part of it's going to transmit and then reflect off the back surface, and that's R2. In general, these two rays are going to be phase shifted one from the other, but if they're exactly one wavelength shifted one from the other, or if their phase shift is exactly some multiple of the wavelength, then they're going to be in phase, and that'll be maximum reflection. So that means that the path length difference has to be some multiple of the wavelength. Now the path length difference is just the extra distance traveled by ray 2, which is twice this thickness L. So we have 2L must equal some multiple of the wavelength lambda, and I'm going to write it by saying lambda times some integer m, where m is 1, 2, 3, 4, etc. But it's not actually lambda because it's lambda in the material. This lambda here is the vacuum wavelength. We want the wavelength in the material, so I'm going to label it as lambda sub n, and I'll just remind you that lambda sub n is just the vacuum wavelength divided by the wavelength, divided by the index of refraction, n. And in our case, it's going to be n2. Now there's one more thing we have to account for, is that there might be a phase shift upon the reflection. So what happens is, when light goes from a lower index of refraction to a higher index of refraction, the reflected ray gets shifted by half a wavelength. So that might offset this whole thing, so we have to correct for it. So let's check. As we go from N1 to N2, we're going from lower to higher. So that means ray 1 comes off half a wavelength out of phase, so we're going to correct for it by subtracting off half a wavelength. Remember, it's lambda n again. So half a wavelength is lambda n over 2, and then we have to see again if there's another phase shift at the back surface. So as we go from 2 to 3, we're going from higher to lower, so there's no phase shift this time. So now we can just solve for L. I'm going to divide everything by 2, and there's a common factor of lambda n here that I can pull out. So we have L equals, then lambda n, which we said was just lambda vacuum over n. And we've got a 2 because we've divided the whole thing by 2, and it's n2. All right, so it's lambda n is lambda over n2, and then we're dividing by 2 because of this 2 that's multiplied here. And then it's times some integer m minus 1/2. And they want the third smallest thickness. Well, the first one would be setting m to 1. That's the smallest you can get. If you go below 1, you get negative. That doesn't make sense. So we're starting counting m at 1. And so the second one would be m equals 2, and the third one is m equals 3. So we set m to 3, and plugging everything in, we can plug in lambda, m equals 3, and n2. We find that L equals 273 nanometers.